Let's see, how come? Okay, I just quickly go through it, okay? If you get a question, last chance to ask, so we'll try to make it clear for you. You understand what it stands for, JFET, right? Johnson effect transistor. And basically, they get only two different types. One they call an N channel, and one will be a P channel. Exactly the same in bipolar transistor. NPN, PNP, okay? And the JFET, you get an N channel, a P channel. And by looking into the arrow here, point in N channel, point out P channel. Okay? And we're talking about JFET, you understand, you can get the current flow here. ID. It will be I at and IG. However, on the time I at equal ID, that is the thing you must know. I at and ID will be the same. Okay? And this is just giving you the physical for N channel and P channel. And this is the N channel. Okay? Okay, so on this one, we don't care about this one now. On this thing here, this is a channel here. We're talking about N channel. Electron will be moving in the channel here. That means the current flowing, depending on more or less electron moving. So when you're looking into that, they measure the voltage VGS and they measure the current ID. Okay, so basically you get the VGS, a negative voltage here, and you get the current flowing here. And this on the picture, second one, you can see you get more negative voltage and VGS, then the current ID will be less. That's only thing I want you to understand. The reason is the channel now will be narrow. Okay, so the less current will be flowing. Okay, on the second one, when you get a less negative VGS, then now you get a more current ID. And if you're looking into this physical here, okay, the channel will be wider. So more electron moving, so more current. Okay, and now when you're looking into this graph right here, the circuitry Okay. N channel. This stands for current ID. And this will be stand for VDS. And this is the current flowing. Okay. So when they reach the point B, you going down, you can see P stands for pin off voltage. When they get to the point B, we start at the VP, and the current ID now will be constant. Okay, and that value will be equal ID at F. So what is ID at X? What is the ID at X? That's the question. How can you answer that question? Okay, you have to tell me. What is the ID at X?
Was that the one where it was drained of source with the gate shorted?
Who can get the definition? You have to know. You have to read the handout to get the correct answer. Only thing you can say, you understand it when I ask the question, you can answer right away. If you still have to open the note, the book, that is not really understand. Okay, I can tell you, IDSS is the constant current maximum when VGS equal 0. Or they can say VGS is shorted. That means 0. Okay, that is the definition for IDSS. If you're looking back into your handout, then you can see it. Okay. And IDSS is not the one you can make it. That's given by the manufacturer. Okay. So if you're looking on this display, they get 3 parts. One right here, before VP, after VP, and a high, that will be a higher VDS. So for this part here, JFET can be using at the resistance. That's what they call ohmic area. From B to C here, ID equal IDSS, that's the constant current. And they call a constant current area or saturation area. Okay, you can see that constant current area. If you increase more VDS, and that's what you get after point C, that will be a breakdown. Okay, we don't care about that part here. We never read that. That's a very, very basic for the current ID. What relation between VP, pin off voltage, and VGS off? Who can tell me? I want to relate. Go ahead. Want the relation, okay, between VP and VGS up.
They have the same magnitude, but a different sign.
Exactly.
In other words, pinch off is usually positive and VGS off is usually negative. So if pinch off is 4 volts, then VGS off is negative 4 volts.
Exactly. Let's see. I want to see how come. Just a minute, okay? Okay. VP and VGS up, they will be the same value. However, they will be opposite. If you know VP, then you know VGS up. Okay. And if you know VGS up, then you know VP. Just opposite. Same value, opposite for the polarity. Okay, so this is the one, you have to read over and over. Okay, what I just asking you, IDSS stands for the current from drain to source with a short gate. That means VGS equals 0. And also they're talking about ohmic region, cut-off voltage. Okay. Cut-off voltage, the value of VGS that make ID approximately 0 is the cut-off voltage VGS off. That only telling you at the VGS off, ID equals 0. Okay. And also they're telling you JFET must be operated between VGS equals 0 and VGS up. Okay. And also relation, I already talked to you. Okay, VGS or VP coming out from manufacturer. But they given you only one. They given you VGS up. They're not giving both. The thing is they equal value, but they just opposite the polarity. Okay, now if you're looking in this display, okay, again, this for ID, This for VDS. And this for VGS. This VGS equal minus 4. This VGS equal 3, minus 3, minus 2, minus 1, and 0. So if you get a point in here, you want to get the ID, you go to ID here, you can get the ID. Basically, JFET will be a voltage controller device. The thing is when you change the VGS, you change the current ID, okay? That will be a current controller. Make sure this is a last chance. I go through again. And if you not quite follow it, understand it, let me know. Otherwise, we don't have a more chance. Okay? And now this telling you this open right here. No current can be flowing. They just given to you. Get a cutoff, VGS, they measure, they equal VGS off. Okay, so that means you see no current flowing. ID equal 0. So make sure VGS equal VGS off. Then ID must be equal 0. And now a little tap in here for P channel. You see that? Arrow point out. The difference between N channel and P channel is for N channel, VGG will be negative. However, for P channel, VGG will be positive. And also VDD in a P channel, they positive, and N channel, they will be negative. That is different. Some question in the handout, that's a standard, example. I want you to know, okay? You have to go through the example. Make sure you know how to do what needs to be done. They say for JFET, given circuit show, they given you VGS off minus 4 volt and IDSS equal 12 milliamp. Okay, so this one we already done. And also we get a solution. You can go to the solution if you don't understand. And let me know. I can help you out. Normally, if you get any question regarding into the on of the handout for the semester, and do not quite understand someone, you can text to me, you want on Zoom. Then I can on Zoom with you to make it clear as I can, okay? So now, JFET transfer for the N channel. This is the display for the current, okay? This is stand for ID, and that will be stand for VGS off. ID equal 0. That means this point right here. And VGS equal VGS off. And at the point here, ID equal IDSS, and you're going down. VGS equal 0. That's what they try to explain to you. And now, basically, this is the equation to calculate the ID. ID equal IDSS times 1 minus VGS over VGS of square. This is represent for this curve right here. That's very complicated, not easy. Okay, on this curve here, this point normally they call a Q point. At this point, you can identify ID, go this way. And also you can get a VGS, you going down. So basically, what they want to know what the ID equal and what the VGS equal. So for each point in here, we call a Q point. And each point on the curve, you can identify ID this way. You can identify VGS, okay? And on the other side, they just showing you what is the value for VGS. Okay, let's see. For the JFET sheet, indicate IDSS equal 9 milliamp, VGS off equal minus 8 volt. Using this value, they want to know the drain current. So if I looking into A, VGS equal 0, then you know right away, ID will be equal IDSS. You don't have to do calculation. And now, number B, they give VGS equal minus 1 volt. In order to calculate the ID, you have to using this formula. You already know IDSS. You already know VGS, they given you minus 1 volt. VGS off given minus 8 volt. And do calculation, you can get the answer. If you get a VGS, then you're able to calculate the current ID by the formula IDSS times 1 minus VGS over VGS off square. Not much the equation, okay? And now they're talking about JFET forward transconductance. The forward transconductance, that means the transfer conductance. GM is the chain of the drain current for the given chain. In VGS, that's a definition. That means you take a delta, the difference between ID divide to the difference between VGS, you get GM. And now, they given you the formula to calculate the GM. GM equals GM0 times 1 minus VGS over VGS off. Okay? And GM0, okay, what is it? Data sheet normally given the value of GMS VGS equals 0, EGM0, okay? So by definition, GM0, that's the value of a GM with VGS equal 0. Okay, and normally the data sheet can give it to you. However, if not given, you can calculate the GM0 here equal 2 times IDSS divide to the absolute value VGS off. You understand VGS off normally negative voltage, and the GM0 just a constant value. So that's why they cannot be negative. Okay. Okay, just an example. Okay, I not go to again. And also example how to calculate the value for input of JFET. That will be equal to ratio between absolute value of VGS to the IGSS. Okay. And you understand for the JFET, it's good to get a very high input impedance. But they don't have any high gain. If they want more gain, better using bipolar, not a JFET. Okay. And now we're talking about DC bias. I just quickly go through that. If you get a question, and let me know. They can get a fixed bias, or gate bias, cell bias, and voltage divider bias. Okay, we don't care much about current source bias. Now, this is a fixed bias. How come they call a fixed bias? That means they get a negative voltage here. Okay, so that will be fixed bias. And when you get a negative voltage here, and you get a resistance RG, will be a high impedance. Okay, so the voltage at the V gate and the voltage VGG will be equal the same. The region A, no current will be flow through the RG, high impedance. So that's telling you voltage here and a voltage here the same. You can say, okay, you don't need that resistor. Just connect directly to VG. Okay. However, they telling you why we need that resistor. The reason is when you converting this circuitry to the AC module, okay, the power supply must be routed. So VGG will be routed, okay? So when you route in here, if you connect directly to the gate, so the sideway coming in, they will be short to the route. They cannot go to the gate, okay? If you get a big resistor here, that means they not short to the route, so the signal can go. Okay, the next show you cell bias. Cell bias, you can say you have a no power supply here. They short to the route. No gate voltage. So VG equals 0. For the cell bias, if you want to do calculation VGS, ID, or whatever, you need the graphic here. That means they have to give you the graphic. Okay. So from this graphic, you're able to find out what ID equal and what VGS equal. Okay. Same thing. Voltage divider, bias. Okay. So voltage divider bias, since the gate source junction has a extremely high in resistance, the R1 minus R2 voltage divider is practical unloaded. Voltage divider bias is more stable than either gate or cell bias. So they want to build the amplifier. For the JFET, first thing they have to go to the DC bias. You can build with the fixed bias circuitry. You can build with the cell bias, or you can build with the voltage divider bias, no matter what, okay? But normally they're using voltage divider bias.
Mr. Pham,
Yeah,
what is the word practically unload mean?
that means that one, they're not loading any signal coming in. You can see this is just a DC bias. And basically, when you build it to be an AC, you get sideway coming in.
Right.
Okay, so they cannot loading that sideway.
Sine wave will not go through even if you had a capacitor there?
Capacitor just be sorted by,
Okay.
you know, for sideway to come in.
Mhm.
However, if the resistance is at the base here, it is small, they will be loading down the sideway.
Mhm.
Okay.
Okay.
However, they're telling you, but voltage divider bias, you don't have any problem on that. Okay, this one for just fixed bias. So if I given you the fixed bias circuitry, and I want to calculate the VGS Q, you understand VGS Q means Q point. The thing is, any point on the curve will be a Q point. Okay, so you think you can do that calculation? They said they want VGSQ, they want IDQ, and they want VS, they want VD. So at least you must know how to do that calculation. Okay, otherwise you can again go to the solution and try to exercise until no problem. VGS equal VG minus VS, and VG is minus 2 volts. VS sorted to round will be 0. So VGS equal minus 2 volts. Okay. And if you want to calculate the VID, and you have to using the formula we given to you already. IDSS times 1. Okay. Minus VGS V over VGS of square. And you get that answer here. And if you want a VD, that means the voltage at the drain using VDD minus ID times RD. Okay. And also VS, you know that equals 0. And also make sure you understand all the time, IDIS will be the same. If you still get a problem for the DC bias, that given to you a really hard time, okay, to get through the amplifier. Now this one, we already get through it. I just make sure, try to telling you what can we do. This is a cell bias. And cell bias, again, they must be given you the graphic here, the curve for the ID. Okay? So in order to solve the problem, what you need to do is you have to identify 2 points, point A and point B. Then you draw the line from A to B intersection with the curve. That's what we're talking about, Q point for ID. You go to the right, you get the ID value. You going down, you get the VGS value. However, normally you open the textbook for technician, they're not using the graphic. If you go to engineering, then you have to do it. Normally, for no matter what the buyer, what they're looking for ID at the Q point and VGS at the Q point. So to get away with the graphic, normally they given this circuitry here, they can give it to you VD value. Then you can do calculation without graphic. Okay? And if you're not giving you VD here, then they can give you VS here. If you get a VS, at this point you can able to calculate the IS. Okay? VS divide IS, you get the IS, and IS and ID will be the same. So that's what you get the ID. Normally, in most of the textbook, they have to do that way. They don't want to deal with the graphic. Okay? And you're looking into that example using graphic and try to see how can you get point A, how can you get a point B, and you draw the line, okay, from A to B in order to get the intersection right here. That's what's called Q. IDQ, go this way. VGSQ, going down here. Okay, any question on this example? I'm not going back try to telling you how to get point A, how to get point B. Try to go through again. If you cannot, that you need my help, okay? Otherwise, take a long time to get through everything. Now, next one, voltage divider. If you get the bipolar transistor done, that's more easy, okay? You see that, you can calculate the VG right here, voltage divider, okay? And basically, they telling you you need a graphic to do it. However, if they don't given you the graphic, then they have to give to you either VD right here, value, or VS right here. Okay, then you can do calculation without using the graphic. And then this is the graphic, how we can get Q point. So you need to identify 2 points. Point A here, point B here. You draw the line, intersection with the curve here. That's what we call a Q point. Go to the right, you get the ID. Going down, you get a VGS. Okay, any question up to this point? And this basically just an example for you guys to do it. Again, make sure you're able to follow example and try to do it. Okay, now you can see solving DC cell bias without graphic. So now they given you this is a cell bias. And now they not giving you the graphic. They given to you what? ID equal 1 milliamp. Okay, so whatever they want to calculate here, VG, VS, VGS, VD, VDS. I already given you the solution. And you have to spend the time. You go through that, okay, in order to do the calculation. And also this is an example, voltage divider. Okay, and I already telling you what to do, what needs to be done. Only thing you have to go through that, okay, to make sure you know how they be working. And also they given to you a next voltage divider bias without graphic. Without graphic, they given to you VD equal 7 volt. So now you can calculate the ID easy. ID will be equal VDD minus VD divided to RD. Okay, so that's what you get ID. And the V get VG right here, voltage divider. Okay, and ID, I just telling you how to do calculation. VS, how do I calculate the VS?
Voltage divider.
What? I want to calculate the VS. You see that in here. First thing, VG, using voltage divider. VDD times R2 divide R1 plus R2. Okay. And on ID, they already given to you VD 7 volt. You can calculate the ID. ID equal VDD minus VD divide RD. Okay. And now my question is, how do I calculate the VS?
IS is almost equal to ID.
Exactly.
Exactly. Yeah.
And what VS equal? The thing in number C, they want to calculate the VS telling me. How do I calculate what formula?
Ohm's law. V 嗰個
Ohm's law.
IR。
They're telling me the formula.
VDD minus IDRD.
VDD minus
IDRD.
I'm not following. I was already telling you. Again, to calculate the VG, voltage divider. VDD times R2 divide R1 plus R2. Okay, that is the number A. Number B, I want to calculate the ID. Then you know ID. VDD minus VD divide to RD. VD already given to you here. Okay.
Okay.
Now, question A. What formula to calculate the VS?
ID times RS.
ID times RS. Exactly. IS times RS. And you understand, IS equal I
G.
D. That's what I want the answer. You know right away how to calculate it. The
I
thing
think
is,
Mr. Sathem,
Yeah.
the formula I said that is going to give the same answer, the formula you are writing. VD, if in order to find out VS, you can do VDD minus IDRD. Same as VS, what you wrote, IS into RS.
okay. VS will be measured from where to where?
VS is from source to ground.
To source to ground. So that's the only way you can do it. Take the IS times RS, correct? That
Right,
means the
right,
voltage,
right.
the voltage from source to the ground.
The voltage from source to ground is
Right.
VD times RS.
ID times RS, the same IS times RS, right?
Right.
That's the thing is, those current same value all the time. You don't have any more different way to calculate the VS. Okay. Number D. They want VGS. How do we calculate the VGS?
VG minus VS.
Exactly. VG minus VS. The thing is, normally interview for technician, you don't have to do calculation, but they asking you how do we calculate it? Like VGS, you know VG minus VS. VG already get done. VS already done. That will be easy to calculate the VGS. And the last one, VDS. VD minus VS. You already know VD. You already know VS. That normally that example will be given in the test. Only I can something, but will be don't given to you graphic. We don't want to solve the problem with the graphic for the technician. So any question regarding into this example, let me know. Okay. Okay, any question anymore? Otherwise, we will go into amplifier. And also, I try to make sure you still memorize, okay? Bipolar, that means the current controller device. JFET, that's a voltage controller device. Okay, the difference between the JFET and also bipolar. JFET get a very high input impedance, but they don't have a much high gain. And also they will be asking you, JFET is an on or off device. Which one? On or off device?
50-50 on.
Can you repeat the question, Mr. Span?
JFET is an on or off device.
It's based on the biasing. It's generally on.
It's 50-50.
It's on devices, I believe, sir.
Okay, now how come you said on device?
Because the current.
He flipped a coin.
The thing is, when if you get interview with me, I asking you that. First thing, is it on or off device for the JFET? And if you say on device, okay. Now, next question will be why you said that will be on device.
What do you mean by on or off device? Are you talking about switching?
That's what they ask. That's what they want you to understand.
Because the gate is normally open, and when you apply the voltage to the gate, then the gate becomes narrow, and then it becomes off device.
Okay, now I'm telling you. Bipolar transistor on or off device.
Off.
Off device.
Off
Why
device.
off? Why off device? For bipolar.
Is based on the flow of the current from the base.
No, that's not the right answer.
Okay.
Transistor works on the voltage, works on forward bias voltage and reverse bias voltage. It's based on the voltage, while the JFET based on the current.
Now,
Have you ever told us what an on device is or an off device? I don't think we've ever heard that term before.
okay, I'm telling you. You see that? Cell buyer. You don't have a power at the gate. However, the FET still working. That's what they call a on device. However, for bipolar, if you don't have a voltage at the base, they cannot work it. Okay?
Okay,
That is, they have to be off device.
yeah,
On this JFET, even you don't have the voltage at the gate, they still working. That's what they call on device. So now you understand what that means for on or off device.
Means by default, JFET is an on device.
Exactly.
and the bipolar is normally off.
Exactly. Without the voltage at the base, bipolar cannot work it. However, without the voltage at the gate, JFET still working. Yeah, if you understand more on the JFET, that's a very, very good. Most of the design at this time they're using JFET more than bipolar.
Hey, Mr. Pham, depending on the application, for JFET or bipolar, how do you know which one you want? Is it based on your application? You want something that's on all the time or off all the time? Or how do you determine that?
Now, basically, depending on they want high gain, they not using JFET.
Right.
Okay. The thing is, only bipolar CE amplifier giving you more gain. However, if they want more input impedance very big, they using a JFET. So depending on engineering, when they design, okay,
Okay.
they have to know which way, which IC, which amplifier they need it. Okay, now let's see. Okay, let's see. I go to the one will be JFET amplifier. Okay. Normally, in order to understand, before we start it, you have to spend the time to read through it. Okay, to get the idea what we're going to cover. That's much easier for you. Even you not design anything. However, the basic you must know. Okay, JFET commonly used to amplify small AC signal. One reason for using a JFET instead of the bipolar transistor is that very high input impedance. Okay. A big disadvantage, however, is that the voltage gain obtainable with the JFET is much smaller. Okay. And the same thing like bipolar. Bipolar, you get the three configuration: common emitter, common collector, common base. And the JFET doing the same thing. They get common source, common gate, or common drain. You can see that very similar. Now, in order to do for the AC analogy, you get the 4 steps, must be remember. First thing, set on DC source to 0 and replace them by the short circuit equivalent. That means on the AC module, you don't have any DC power supply anymore. They short it to ground. Number 2, replace on capacitors by a short circuit. Okay, that means in the AC you don't see any more capacitor. They just short it. Okay. Number 3, remove all elements bypass by the short circuit equivalent as introduced by step 1 and step 2. Redraw the network in a more convenient and logical form. That is the process before you start with the AC module. Now, this is the JFET AC. This is the JFET for DC. This is the JFET for AC. You can see this is the gate, this is the drain, and the short here. Okay. Now you can see from the drain to the short, you get the current. Okay. And that current value equal to GM times VGS. Okay. This is the VG, this is the VS right here. So from here to here, that's what we call a VGS. Okay. And also inside the JFET, you can get a resistance RD. Okay. And we never using RD. The thing is RD will be too big compared to external connection resistance here. Okay. So we forget this resistor. Okay. Now you can see JFET input impedance equal infinity O. That means very big resistance. JFET output impedance. Okay. So basically they equal, we call it G0. Okay. RD equal 1 over. Okay. Lambda 0 X, but we don't using this one, where lambda 0 X is a component of an admittance equivalent circuitry, normally at the range of 10 to 50 microsiemens. Now let's see. Common source. First one, we go to a common source amplifier. Common source amplifier, the input will be applied to the gate and output will be from the drain. Okay, that's what we're talking about common source. When you're looking into the schematic, you're able to recognize what type of the amplifier, common source, common drain, or common gate. Okay. And if you're looking into this circuitry, what bias they using to build the amplifier? What type of the DC bias?
Oh, you mean like fixed bias or something?
No, what I'm saying is, when you're looking into this schematic, what type of the DC bias they using to build the amplifier? They can build by fixed bias, they can build by cell bias, they can build by voltage divider bias. So which one?
Fixed
Self
bias.
self bias.
Hey, what?
Self,
What you get here?
okay.
Power.
So what type?
Fixed bias.
Fixed bias.
Right, yeah.
Okay, that is the first thing you must be recognized. They can build the amplifier either by fixed bias or cell bias or voltage divider bias. Okay, on this common source, they using fixed bias. On different textbook, they can using cell bias, or they can be using the voltage divider bias. That only telling you, before you go to the AC module, you have to calculate everything for the DC bias. If you don't know what type of the bias, then you cannot do calculation for the DC before you can do for the AC. Okay, so that's why I already explained to you here using DC fixed bias. And they can be cell bias or voltage divider bias. Now, input signal applied to the gate. Output is taken from the drain. And also they're telling you input, output will be out of phase. That is summarized for you. Okay, the thing is you don't have to do any calculation for the AC. But basically, when you're looking into schematic, you're able to talk. And basically, how do we know that a common source? Based on input, where output, okay? And also, input output will be our phase. That's the minimum thing any student learning JFET must know. Okay, and this is the input impedance. That means your source right here, input here, when you're looking into the amplifier. That's what we're talking about, input impedance. And this is the output when you're looking from output to the amplifier. That's what they're talking about, output impedance. Okay, now, you see, I converted circuitry to AC. First thing, you don't see any capacitor here anymore. You see that? This capacitor C1, no more. AC, they just sorted. Okay? And DC power supply battery, minus VGG here. You cannot see any VGG. they short it to the ground. Okay, you can see that battery VGG is replaced by shorted. And in the dark area here, inside that JFET, you can get the current flowing from the drain to the source, the value GM times VGS. And I don't have any R small d here, internal output resistance. We don't care that. And now you can see RD. Okay. What is RD from this circuitry here?
Resisted.
You understand? VDD here will be routed, right? On off the DC voltage must be dropped. So that from the drain to the ground, you get resistance RD. Okay, drain resistance. And you cannot see any more C2. C2 will be shorted.
So, Mr. Pham, you're saying if you had a resistance on the other side of that, since that voltage was shorted, since the capacitor was shorted, then it's in parallel. If it was another resistor there.
You don't have any load resistance for this circuit.
But if it was one there, they would be in parallel.
Exactly. If you get a loading, right now, this circuitry no loading. They just try to replace this circuitry to the AC. You have to follow the 4 steps we just talking to you. Battery will be shorted. Capacitor shorted. So that's why VDD no more, shorted to ground. So that's why at the drain, you get the RD connect to VDD, now connect to the ground. And the capacitor C2, no more here. They shorted. That's how the circuitry look like for AC. I want to know any question, anything converting from the DC circuitry to the AC circuit. Okay, now you can say that AC module. If they want to do in calculation, for example, if you want to calculate the V out, that means output here, V out. V out and the current flowing here. The value will be GM times VGS. V out will be measured from the output here to the ground. However, the current flow this way. Voltage and the current opposite. Okay, that's why the output will be our phase. Okay. So the V out will be GM times VGS. That means the current right here. Times the current in this one output impedance equal RD only. If you get a load resistance here, then you have to combine the load resistance and RD to get the output impedance. They want to calculate the VGS. VGS, that means voltage from G to the S. And VG and the V in, same thing. Okay, so VGS equal V in. Okay, then V out equal GM time V in time RD. Current and a voltage opposite, so that's why they get a minus here. However, for the AC, you're not using the negative. The thing in AC will be very positive than negative and keep going. So only thing they can tell you, input output will be out of phase. Input positive, output negative. Input negative, output will be positive. Okay. And also they given to you AV, the gain voltage equal V out divided to V in. And that equal minus GM times RD. If the load included, then the gain will be equal minus GM times RD parallel with other load. So now that they given everything you need to know in order to calculate the output, calculate the gain, okay? You better go through that, okay? Try to say you can understand. Okay, any more questions? If it's not, what I want you to do, okay, tonight, you try to get the time to go through this calculation example, okay? And I will be talking about that tomorrow. Okay, up to that point. You get any question, let me know.
Yes, teacher, I have a question.
Yeah, go ahead.
So in these devices, the gain is going to be affected by the load.
The gain will be affected by
The load, the
IL.
RL, yeah?
Yeah, if you get the IL, then the output impedance, they different. In here, you can see gain time RD. The thing is on this one, you don't have the load. Okay? That means output impedance. So now, if you get on the, let's see, here, you can see that. This one, you get a load at the output. So the output impedance, you're looking in this way. You can see you get a RD parallel with RL. So the output impedance will be RD times RL divided RD plus RL. So the gain now will be different. Okay?
Okay.
The gain will be equal minus GM times G out. This is just applied for the circuitry they give it to you right here. G out only equal RD. If GL equal combination between RD R load, then you have to calculate the equivalent. Okay?
Okay, thank you.
Yeah. Okay, so if it's not any question, then will be good night to everyone.
Good night.
Good night.
Good night.